So today we are going to talk about an important aspect in SQL Server. If you remember, like 3, 4 classes back, we talked about different type of functions that we have in SQL Server. At that time, we talked about the ranking functions, right? So we talked about that there are some functions which are known as the ranking functions or the Windows functions in SQL Server. So if we talk about the ranking functions or the Windows functions, there are in total 4 different functions in SQL Server, which are known as the ranking function or the Windows functions. So the first function in that regards is the row number, the second one is the rank, third is the dense rank, and fourth is the end type. Each of the functions are having different purpose, right? So we are going to understand about the details of each one of them. Let's first talk about the row number function. The row number function computes a unique sequential integer starting with 1 within the Windows partition based on the Windows ordering. Note that the ordering isn't unique, the row number is not deterministic. For example, notice in the results that the 2 rows having the same ordering value here, but the 2 rows got different row number. So let's understand this with example, all of this, right? So for going through the examples, I'll create a temporary table here and I'll insert some values into that temporary table. So let me go to the batch 266 database. There I'll create a temporary table first with 2 columns. I'll insert the value into that temporary table and then I'll set the value. And then I'll apply the ranking function on top of that. So you can see here that this is the value of the column 1 and column 2 that I've got, and this is the value that I've inserted into this duplicates table. Now, the next part of it is to apply a row number function on top of that. So here is the syntax of the row number function that we write. So I'll write select call 1, call 2, then row number. Because this is a function, this should come with parentheses. So row number over, then in brackets, partition by call 2, order by call 1 as row number from duplicates. So if I do this on this table, as of now, you can see that I'm getting all these values. I'll get definitely the same value, but there would be additional column here with the name as the row number column, and where we'll get some row numbering. So let's see what is the numbering that we are getting. If you see here, what we are trying to do is that we are partitioning the records on the basis of column 2. If you take a look on the column 2 here, the first column, it has the first row, it has the value A. So for that, the row number is 1. That is fine. Now, because we are partitioned on the basis of column 2, that means wherever the value would be same. So if you see for the next 3 rows, the value of the column 2 is same. So if we do something for this three rows, we have partitioned on the basis of column 2. That means it will define a ranking on the basis of this partition. So it will consider all of these values in the same partition, and then it will define the ranking. So how it will define the ranking? On the basis of this column 1. So as the value of the column 1 is also same for this 3 rows, so that's why there is no proper, you can say that there's no proper guideline about how this should be ordered and all. But if you see, because the values of are these three are same, so that's why the row number is 1 2 3. Now I'll do one more thing here. I will update the values on the basis of that. So let me do one thing. Let me create another table here just for better clarity. So I'll drop this table once, drop table, duplicates. So now I have dropped the table duplicates, right? So here I'll give it a number 3, 4, then 5C, 6D, 7D, 8D, E, 9E. I'll keep one 5E as well, just to show you some duplicate values like that as well. Now I'll again create this record set. Now you can see that there is some variation. Only this 5 is getting repeated, and I have kept that intentionally here just to show you how what happens when we are ordering on the basis of that column, and that column is having duplicate values. So I'll just execute this query for now. Now if you see the execution here, so again for the column 1, you can see that the first value is 1A, so that's why the row number is 1. Now, wherever there will be duplicates into the column 2, because we are partitioning on the basis of column 2, we'll get a row number for each of the values in that column. And also, we are ordering the data by column 1. And when we don't mention that on which, whether we are doing it ascending or descending, it would always be ascending. If we want to do it descending, we need to tell that to SQL Server. So as it is ascending now, so here 2, 3, 4. That means it will become 1, 2, 3, because the value is same for this three rows. After that we have C, which will again become row, because the row number again will start from for the next partition, it will again start from 1. Then if you see there are 2 values for D, so that's why it's 1, 2. Then 3 values for E. When we are going for E, definitely the first value here will be 5, because again 5 is the lowest in the column 1, and we are ordering on the basis of column 1 ascending. We have not mentioned ascending or descending, that's why it's ascending by default. If I want to do, I can do it on the basis of descending order as well. So I can put here column 1, then descending. What will happen after that? This 9 will have the first row number, then 8, then 5. This is what will happen for this set. Again for this one it would be 4, 3, 2, something like that. So I can show you that as well. You can see that now this row number for 4 is 1, for 3 it's 2, and then for 2 it's 3 for the same set. Then if you go for D, again it's like 7, 1, 6, 2, right? So this is how the row number function works, right? So this is useful in such a scenario when you are trying to get a record, get record sorted on the basis of something. For example, sometimes we get the scenario question like you want to find the top five records on the basis of salary for each department in the employee, right? So we'll have the employee table, department table, and if we want to get the top 5 employees who from each department who have the most salary, right? So what you'll do is that you'll partition the data on the basis of department, because you want to get that for each department. That means for each wherever you see the each word, that is your partition column. So here you want to get the data on the basis of each department. That means partition by department ID or department name, whatever is there in the field. And then order by salary. And you want to get the top 5 salary. That means it would be salary descending, because again, you want to get the highest salary. And then out of that record, what you can do is that you can fetch out the only 5. So for that, you will either need a CTE or something, or you can just filter on the basis of subqueries. So this is how we solve such questions where we are trying to get, any number related thing, top 5, top 10, something like that. So let's go forward and let's talk about the other function here, which is the rank function. The rank function returns the number of rows in the partition that have lower ordering value than current plus 1. Rank differs from the row number in a sense that it assigns the same ranking values to all the rows that share the same ordering values. So there are difference between rank and row number function, and again rank and dense rank function. Let's talk about dense rank as well, because again from the definition it won't be very clear to you guys. Again from the example only we'll be able to understand what is the difference between rank, dense rank, and all of that. So let's talk about dense rank function. Again, the dense rank function returns the number of distinct ordering values that are lower than current plus 1. Because rank considers rows and dense rank considers distinct values, the former can have gaps between result ranking values and the latter cannot have gaps. So this point is the major difference between the rank function and the dense rank function. What is the difference between them? So the difference is like, so for example, we apply a rank, right, and two values are same, then the rank of both two values would be the same. But after that, when we go for the next ranking, rank will get some skipped value. That means, for example, for two of them, we had the rank like 5 5. After that, rank will give the ranking 7 for the next value. It won't give 6 now. 6 would be skipped because it gave 5 two times. But what will happen in case of dense rank is that will get uh, after 5 will always get 6. So that is the major difference between rank and dense rank function. Let's understand by example here. So here for this one, we have done the row number. In the same way, I'll do the rank over. So this is the, I have defined here the rank number. And in the same way, I can define the dense rank function as well. So here I'll write dense rank as, so you can see that now I've got the value for the row number, rank, and dense rank, all of that, right? So what is happening in the rank? We are partitioning on the basis of column 2 again. So if you see the column 2 here, so here, and we are ordering on the basis of column 1. So if you see here, um, now let me make it as ascending as well for better readability. So if you see for this particular instance, we are getting the same value for this as well. We are getting the same value for this, and we are getting the same value for this, because everything is partitioned on the basis of column 1, column 2, and that's why the column value wherever it is same, we are getting the same row number, same rank number, and same dense rank value. So there is no difference between all of them here. But what would happen in a situation where we this example is definitely not the perfect example to cover rank and dense rank, and because right now you understand that this is all the uh, same thing here, right? So let me just uh, get through AdventureWorks and let me give you an example of rank and dense rank in terms of AdventureWorks database, so that you can actually understand the difference in, and you should understand that in which scenario we should be using rank, in which scenario we should be using dense rank, and in which scenario we should be using uh, the row number function. Now, one thing for sure is that for this particular example that I have taken here, so we should be using the row number function, and I'll come to that later on. Let's first go into the AdventureWorks 2019 and let's again try to find out something where we can try to understand the difference between rank and length, right? So what we can do here is that select, I'll just select star from some table name here, human resources dot employee inner join. I'll give it a name E, inner join, human resources dot employee department history, EDH on E dot business entity ID equal to EDH dot business entity ID. And then I'll select few columns from both the table. So from this one, I'll select E dot business entity ID, E dot hire date, E dot job title. Then let's select some column from EDH dot department ID and then EDH dot shift ID. Let's see what data we get from this. As you can see, for some of the job titles, the department ID is just the same, right? So what we can do is that we can find that we can get the ranking on the basis of that, and also on we can order on the basis of hire date and all. So let's try to do that. So here for this particular example, what I'll do is that I'll put a rank number function here. Okay. One more thing here, the partition by thing that we are writing here, that is totally optional. So if we don't want to partition on the basis of something, we can do that as well. So I'll come to that. I'll show you that as well. But as of now, I'm going to do the partition by department ID. That means EDS dot department ID, and then order by hire date, E dot hire date as rank number. So the same thing I'll copy here for the dense rank, because we also want to understand the difference between rank and dense rank. So dense partition by as dense rank number. So let me run this query now. What we see here is that this particular okay. So if we see here, so we what we have done here is that we have done the partitioning on the basis of department ID, right? So this all department ID are same, right? Right. So if you see, because this is the our partition for each department. So for each partition will have a different ranking, right? So as each of this partitioning is same, each of this department ID same, that's why we have the different ranking from 1 to 7 for this, and the same for dense rank, right? And if you see this value, this is actually different for each one of them, and that's why we have a different ranking. Now if we come down here for this particular one, please pay attention to this one. Here the department ID is 3, right? From here to here, I have the department ID 3, right? This is all department ID 3 from here to here. Let me scroll a little up so that this is clear to everyone. Okay. So from here to here, we have the same department ID, right? So if we also see here, from here to here, like the hire date is different. From here to here, the hire date is same, while from here to here, the hire date is again different. So if we go for this one, right, what you see is that the rank number for this is same and dense rank. So rank dense rank is same till here, till here, till here. And but when we come for something where we have a different job title in altogether, That means we have the different higher date. What is happening is the rank number is becoming 12 while the dense rank is becoming 4. So that is the difference between the rank and dense rank. What what we see here is that rank will skip all the intermediate ranking if there's a common ranking for two different rows. So that is what is happening. In total, this is the 12th record, and that's why rank had one rank, two rank, three rank, and after that three was repeated a number of times. Finally, after that, it was remembering the count, and after that it it brought on the ranking as 12. While the dense rank, it doesn't need to remember the count. So it will just go for one, two, three. After the three is over, the next thing would be four, right? So there are some situations where we need the continuous ranking. That means after three, we need four, but there are some situations where we need the final ranking. That means after three, we need 12. So in the situation where you need something like that, then you'd be using rank function. In situation something like that, you'd be using dense rank function. And how we get such question, we'd be getting like, so it would be like you don't need to skip any rankings in between. Something like that is mentioned. That means you need to use the dense rank function, because in rank number function we'd be skipping the ranking. So after three, we are giving the next ranking, which is 12. So depending upon the situation, we have to use a particular rank function. Now, as I was mentioning, we can actually remove this partition. Right now, what I have done is that I have partitioned the whole record set on the basis of department ID. And that's why you see the rank number is actually repeating across. So here it's going from 1 to 7 because this is one partition, and then again it is going from 1 to something. But if we don't want that, what we can do, we can remove this partition thing. I'll remove this partition by clause. Order by clause is definitely required there, but the partition by clause is optional, so we can remove that. I remove the partition by clause from both the rank and the dense rank function, and now you can see that we don't have a partition, but still this is working fine. And now it's working without a partition. That means it is working just on the higher date. So if you see, the record is all sorted on the basis of higher date. So wherever the higher date is minimum, I'm getting the rank number as 1, and it is going on like that. If you see, these two higher date are same, that's why we have the rank number same for these two, but after that we have 12 here. While for this one, it's like 8, 8, and then after that 9. So this is the difference between rank and dense rank function. Next comes the last ranking function, which is not used a lot, right? So we don't use it normally in the normal scenarios, but still, because this is a type of ranking function. So again, we are going to talk about that. So the the name of this ranking function is the antile function. So antile is again a different type of uh, ranking function which we use in SQL Server, right? So through entile function, what we do is that we actually define the query in terms of different ties, right? That means we define the queries on the basis of blocks and all. So we create different partitioning set. So let me show you the entile thing as well. So for example, the same query, what I want to do is that I want to do entile and then 10 over partition by edh dot department id order by e dot higher date. Suppose that I write something like that. Now here, what the difference that you have seen here is that I've given the entile 10. I'll give it entile number. If I execute this, I'll get the value for the entile. Now what happens with entile is that entile actually divides the the whole subset of the records that we select on the basis of some tiles. Can we run this entile as well without the partition by clause, like we have done it for the other queries? Can we do that? Let's try that as well. So here again, the entile I have written without the partition. If you see here, now we don't have any partition. That means we are doing entile on the basis of just the higher date, right? And we have keep, kept here entile 10. What is the meaning of this 10 here? So let's try to understand that as well. So if you see here, if I go until record 30 records, why I said 30 records here. So if you see till the record 30, the value of the entile is 1. Then after 31 to 60, you will see that the value is 2. After 61, it would become 3, right? And the last value for this entile function would be 10. So this is the meaning of entile number here. Whatever the number will give, so what it will do, SQL Server is do, it will calculate the total number of records. So the total number of records is here is 296. It will divide it by 10, which is the value I've given, which comes like 29.6. So it will convert into whole number, which is 30. So it will create a tile of each of the tile of the size 30, and it will give the same ranking to each one of them. And that's why for first 30 records, it's like 1. So if I convert this to 100, what will happen in that case? So it will become like 296 divided by 100. That means 2.96. That means 3. Right? So we'll have a tile of each of the size 3 here in that case. So you can see the first 3 is 1, then 2, then 3, and likewise. So in the normal scenario, there should not be a requirement for the entile function. I don't know when is the last time I've used this entile function in a normal business scenario, right? Because we don't get a requirement. But this rank function and the dense rank function and the row number function, these are the functions which are used a lot in the normal business scenarios. Any questions so far on rank, dense rank, entile, row number? No question. Okay, let's move forward and let's talk about the other thing, which is SQL Server indexes. In SQL Server, one of the way to improve the performance of the query is to create indexes. Now, what is the index? So I think we have already talked about indexes in the past as well, right? So when I was giving the introduction of various terms, I talked about indexes as well, if you remember. So how I normally say that the indexes are, so you all must have seen the dictionary, right, in your houses or the telephone directories and all. So how we were actually able to search the things through the dictionaries, that we had an index page there in the dictionary. In the index page, we'll actually know some of the pointers about how the data is being stored in the dictionary, because the dictionary is normally of maybe 1,000 pages or more than that. So how to get the information about the records to the dictionary? So for that, we need to just go into the index page and we need to find out some pointers to the data. And then we go to that page finally and we get our data, right? That's how we search. Similarly, for the telephone directory that we were using, you do the same thing. We'll go into the index, we'll search by the name, and from there, sorry, excuse me. So this is how we search through the uh, uh, indexes. So indexes in the database are actually the same thing. So we have two type of indexes in database. First is the cluster index, and second is the non-cluster index. These are the major classification of the indexes in the database, right? The first one is the cluster index and second is the non-cluster index. Now, what is the difference between these two indexes if these are the major indexes, right? So if you remember, as of now, what we were doing, whenever we were creating a table, we were defining a primary key to that table, right? By default, the nature of SQL Server is like that. Whenever you define a primary key to a table, SQL Server creates a cluster index on that table. For example, I'll create a table here. create table salesman ID int identity 1 comma 1 and then name varchar 50 salary money constant pk underscore salesman code id primary key, right? So if I define this table salesman where I've defined ID, name, salary, three columns, and then I've defined a primary key on this table on the which column on ID column. So now as you can see, my table got created. Let's see this table in this explorer here. So I'll go to batch 266, I'll go to tables, I'll go to salesman column. Here, if I see the different things here, you can see that ID is the primary key integer, not null, because primary can contain the null values. If I see the keys here, I have defined the primary key pk underscore salesman ID, which is again situated here. If I go to the indexes, what we see here is that there is an index already created with the same name and it's given as clustered. So as I was saying, whenever we create a primary key on a table, by default, a cluster index is automatically created. Why it is created? Because this is how the primary key works inside SQL Server. What happens in a primary key? So primary key will always contain a unique value, right? And also it won't contain any null value. The same definition is for the cluster index as well. It will always have the unique values and it won't contain any null values. And what happens inside the database when a cluster index is created? So what happens is that first of all, the data is sorted on the basis of the column on which the cluster index is there. For example, right now we have the cluster index on the basis of ID column. So whatever the data would be there in the table, the whole data would be sorted on the basis of this ID column, because this is the column on which I've defined the index, right? And again, it would be physically stored in the database on the basis of that sorting. So this is what happens in the case of cluster index. And that's why whenever we are searching data and we are using the cluster index, actually the data access is faster, because SQL Server, it will again restore the all the data on the basis of the cluster index columns. It will physically store that data, and that's why the cluster index traversing through the cluster index is always faster. So that is about the cluster index. What about the non-cluster index? So non-cluster index, SQL Server will not store the data in the physically. It will not store on the basis of non-cluster index column, but what it will do, it will logically arrange the data on the basis of non-cluster index columns, and again it will take the address of the data as well. So it will not store physically, but it will actually store the address of the data in the non-cluster index on the basis of the column that we have. Will find out the We'll try to store the address of each of the column, like we are storing in the dictionary and all. So in the dictionary, what we do is that we don't physically store the data in the index space, but we just store the address that where this data would be stored. And then we go to that address based on this information that we have, and we find out the actual data. The same way the non-cluster index actually works, right? So this is the difference between the cluster index and the non-cluster index. Let's talk about some of the other things here. So these are the different type of things that we are going to learn about in this session. The first important thing is the B tree. We are going to talk about what is a B tree. Now for that also, I'll come here, right? Suppose that we have 1, 2, 4, 8, 10, 20, 32. This is the data that we have in the table stored. Now, right now, we don't have any index on this table. What will happen whenever you'll put a select statement to select some data? SQL Server will actually go one by one and it will search for the data. This is how it will go one by one. And this search is known as linear search. When we don't have any indexes on the table, then SQL Server searches the data on the basis of some linear search. When we have the index, all this linear search is actually converted into B-tree search. So for example, here we have all this different type of records. What I'll do is that in case of B-tree search, I will just put this 8 as the, suppose that 8 is the root node of this. After that we have, so if we talk about what is lower than 8, so we have 4, then we have higher than 8 is 10. I'll just come to how I came to all of this. So here less than 4 is again, it would be here 1 and then 2. And then if we talk about 10, we'll have 20 here. Let's suppose here we have 20, then we have 10, we have 32. Okay, so this is how the data would be stored in case of when we have the indexes. So now this is the index table, which is also known as the B-tree structure. So this is how the B-tree looks like. Whenever we create an index, a B-tree structure would be created. For example, you are looking for 32. Okay, you are looking for 32 here, right? So when we didn't had an index here, what will happen is that how SQL Server will look for 32, it will check whether this value is 32, then this, then this, then this, then this. How many times it searched for getting 32? 1, 2, 3, 4, 5, 6, 7. It searched for 7 times to get 32, right? Now suppose that we have the index on this table and we are still looking for 32. Okay, then it will come to 8 first of all, because 8 is the root node. So because it's from where the data is starting, so it will come to 8. What happens in the B tree is that whenever we go on the left side, we'll have the less data than the root, and whenever we go to the right side, we should have the more data than the root. That's how the B tree works. So it will come to 8, it will compare 8 versus 32. It will find out 32 is more than 8. So it will go to the right side, 20. It will again search here. So again, 32 is more than 20. So it will again go to the right side. So here, and it got 32. How many times we searched here? Only 3 times, right? Here we searched for 7 times, while here we searched for 3 times. And this is the reason why indexes works faster. Why? Because the data is converted from linear search to B-tree search. And now, whenever we are in the B-tree structure, you won't have to go and you won't have to search for that much time. You'll get the data in a faster way. For example, we are looking for, suppose that 20. For 20, we'll have to search here 6 times, right? While for 20 here, we'll have to search just 2 times. It will just come to 8 and it will compare 8 versus 20. 20 is more. So it will come to here on the right side, because whenever we have data more, then we'll go on the right side. Whenever we have less, then we'll go on the left side. This is how it works. So it will go here and it will find 20. So 20 equal to 20. We got the data with just 2 searches. So always, most of the time,
B tree would be more efficient. But there are some conditions as well where actually the linear search is better. For example, suppose that we are looking for one and the data is like this. So in that case, whenever you are going for linear search, you'll just search for one time and you'll get the value one. But here, for getting the value one, you'll have to search three times. But again, the other thing here is that here the maximum time you are searching is three only for getting any data. While here you have the either seven times, six times, five times, four times. So it can be anything. So index is a set of key address pair. That is what the index is. It associates a set of objects into orderable quantities. Indexes provides random access to the records. These quantities are smaller in number or provide a mechanism for faster search. So index would always have a key value pair or key address pair. Key address pair means the key would be the column on which you have the index, right? And the address would be the location where you'll have the actual data. This is how the index looks like. If we talk about the index architecture, as I was telling, we have two type of indexes. We have the cluster index and the non-cluster index. Talking about the cluster index, it is a method to store data derived from one or more table in a same block. A printer, a printed phone directory is a great example of a cluster index. We need to index the clustered. This is a special type of index that records the way records the table are physically stored in the table. That is the reason for restriction of only one index per table. So if we talk about the cluster index, we can have just one cluster index per table, right? We can't have more than that. Why? Because there can be only one way through which you can physically sort the data in that and store it in the table, right? There can be just one physical sorting mechanism for any data. For example, uh, let's go back and let's talk about uh, this human resources dot employee table that we have. So I'll just select all data from human resources dot employee table. So if you see the business entity ID column, that is unique, right? So suppose that I define the cluster index on this column. So what will happen is that the whole data for this table would be sorted as per this column because I've defined the cluster index on this column and it will be stored physically. Now, someone can say why we can't have another cluster index here, because the rule of the cluster index says that whenever you create the cluster index, the data would be sorted as per that column and it would be stored physically somewhere, right? So now if I define another cluster index, right, then what will happen? Suppose that I define it on the basis of this national ID number. What will happen now? The data will be stored physically sorted on the basis of this column. So that will actually violate the rule for the cluster index because we had already a cluster index and we had defined this data physically sorted on this column. But now we are saying that we are defining another index on the same column, uh, on the different column, and we are physically sorting the record on the basis of that. So that won't be true, right? Because we won't get the same sorting order with the different column, and we can just store physically in one way, right? So that is why we can have just one cluster index per table. So again, talking about how the cluster index is used, how the non-cluster index is used, and all of that. So let's do an example in the AdventureWorks database, right? So in the AdventureWorks database, we have the sales order detail table. I'll run this query, and also I'll show you how can we see that how to use the indexes and all, where we can see all this information. First of all, I'll execute this query just like that. You see that I got 28 records, and two columns are here. One is the sales order ID and sales order detail ID, and this is the name of my table: sales dot sales order detail. where I'm searching on the sales order ID equal to 58950. Now let me go to AdventureWorks 2019. Here I'll look into sales order detail. So this is the table. These are the columns. If you see here, we have defined some indexes as well and the primary key here, right? So these are some of the indexes that we have. If you want to see the definition of index, there can be many ways, right? But normally whenever you define the index, you write it like table name, then the column name on which you have the index. If you see, the primary key of the table is also index, right? I have already explained how primary key is a cluster index and all. So the primary key of this table is on sales order ID and sales order detail ID. These are the two columns on which we have the primary key. So here we have a composite key. When we have primary key on multiple columns, we call it as a composite key. So here we have a composite key primary key. That means we have the primary key on combination of two columns, sales order ID and sales order detail ID, right? And here in the where clause, I have just used sales order ID, not the sales order detail ID. So if I execute this query, it takes some microseconds and gives me the result. Now I want to know whether my index are used or not in this searching this data on this query. The other thing also I wanted to mention here before going into further into indexes and all, that indexes are useful only in selection of data. They are not useful in insertion, deletion, or updation of data. That means whenever you are using the insert, update, delete statement, the indexes won't be used. It would only be used in case when we are selecting the data, right? So that is one thing. Indexes act as an overhead when we are inserting, updating, and deleting the data. So that is another thing. That's why we should not be creating a lot of indexes. Too much indexes is also harmful. Why? Because when you'd be selecting the data, definitely indexes would be helpful. But when you'd be updating the data update has to go into indexes as well. When you are deleting the data, the same has to be updated in indexes as well. When you are inserting the data, the same has to be updated in the indexes as well. So that's why indexes act as an overhead when we are doing the insert, update, delete. Now talking about this particular uh, query. So here we have this include actual execution plan button in SQL Server Manual Studio. You can see the cursor, my cursor here. So if I select on that, I have now selected that include actual execution plan, right? So now if I execute my query, I'll get the execution plan as well along with the result. You can see that I've got another window here, which is the execution plan. So execution plan, in the execution plan, we can actually know whether our indexes are being used or not. What is how the query is being called and all. So if you see here, I can see that the cluster index seek is happening here, right? So there are three type of operators here that I want to tell you guys. One is the index is seek, which can be either cluster index seek or non-cluster index seek. In the same way, we can have index scan, which can be again clustered and non-cluster index scan. And then we have the table scan. Let's talk about table scan here first. So suppose that we have 10,000 records in the table. And SQL Server is actually searching through all the records of the table because we don't have any indexes on the table. Table scan would come into picture when we don't have any supporting index on that table for that query, right? So in that case, SQL Server has to search through all these 10,000 records to get the data. Then lower than that is the index scan, which would be used. Suppose that we have the 10,000 records and we have indexes which is having 1,000 records, right? So when SQL Server is searching through all those 1,000 records, then we call that as a index scan. Then the last part of this is the index seek, which is just like suppose that we have 1,000 records in the indexes and we just search 10 records out of that. That is known as the index seek. So index seek, as you can see, that is the best operation. Why? Because it is searching the lowest number of records to get. This is just an example I'm taking. It's not, true. I'm just trying to say here is that when we have the index seek, that means SQL Server is searching for the least number of data to get the record. That's what it means. So index seek is something like where you are searching the lowest number of data. When you are searching through the whole index, that is known as index scan. And when you are searching through the whole table, that is known as the table scan. So these are the three different things. As you can see that here we are having the cluster index seek. That means we are just going through the least number of just only the part of the index to get the data. That is known as the cluster index seek. So this is one of the best operation here, right? So here we have the cluster index seek. Now there was another operation here, which is like this, which is coming as a cluster index scan. So let me just copy this query and run it there and see the execution plan. So this is the other query. I'll execute this. I got this result, and this is the execution plan for this. So you can see that I'm getting the index scan here, not the index, right? So now the question is that we have the index on the basis of sales order ID and the sales order detail ID, right? But I'm for the sales order ID filtering, I'm getting the index C, while for this one, I'm getting the index scan. Why it is like that? So before going to that, let me tell you one thing that indexes works on the filtering of the data. So whenever you are trying to create an index, on which columns you should be creating the index? You should be creating the index on the columns on which you are filtering the data. That means the where you have the where clause, where you have the join and things like that. These are the columns on which you create the indexes. So we have done the same thing. We have created the index on the sales order ID column, right? You can see there. And we have also the index on the sales order detail ID. Now, if I see the definition of the index, this index, particular index, let me go and let me open the definition of this index. What I'll see here is that the first column for this index is this one. And this is in the ascending order. By default, this is the order that SQL Server follows, the ascending order. And this is the second column, right? So if we have the first column being used in the where clause, the index C could be happening. Why? Because the data is sorted first on the basis of this column. If this is missing, if we have the second column only, then SQL Server is not going to do the index C. Why? Because this is the second column in the index. Always the first column should be there in order to use that particular index. So in order to convert this query into the index C, what I can do is that I can put here after where one more clause here. Says order ID equal to this and this. So if I write that, I'll get the same result. But what will happen? This converted into C. How it converted? Because I saw the definition of the indexes and accordingly I tuned my query. So this is not the ways always. This is very advanced. So I would say that even if people have 6, 7, 8 years of experience in the industry, it's hard for them to understand this concept sometimes, right? So I would say that 90% of the people don't understand about indexes in the database industry right now as well, while I'm talking about all this, right? So this all comes with experience only. I have decades of experience working onto all of these, and that's why I'm very comfortable with all these different type of topics and all, right? So, what I ask you to actually go back and try to understand, try to do the same queries, try to run, try to see what is happening inside, try to run some other queries in the Adventure Works database and see the execution plan, what is happening, and you can then ask the relevant question on the basis of that if you have. But I think even if you have the basic knowledge about what cluster index seek, what is scan, what is table scan, what is cluster index, what is non-cluster index, right? how to understand the execution plan. This is another important thing. So how do we read the execution plan? So we read the plan by bottom to top. That means here right now we have just one single thing here, but it can, vary. It can become very complex as well. So how we read it? Bottom to top and then right to left. This is how we read the execution plan. Bottom to top and right to left. This is how we read the execution plan. So we'll talk about that. So this is how we create the index again. This all different type of indexes we can create: the unique, clustered, non-clustered. Now it can be unique clustered as well, unique non-clustered as well. That is totally optional. The column names and all, right? So for example, if I have to create an index on any table, right? For example, we have that salesman table that I had just created 2 minutes back. Let me see if I have that. So this is the salesman table that I had created, right? So let me create a non-cluster index on this table. So create index ix underscore the name of the index. So this is how I try to name, but this is not a general rule. I put ix then table name then column name. For example, I'm creating it on maybe salary. Okay. So create index name. Okay. On we put the on clause on table name. So the name of the table is salesman, and then in brackets we put the column name on which we want to create the index. So I just want to create it on one single column, salary. And if I click on this index would be created. This is a non-cluster index. If I want to create a cluster index, I'll have to put create cluster index. But because we already have the primary key on this table, so I already have the cluster index created. If I want, I can drop that index and then I can recreate it. The other thing here is that again, if I want, I can drop this index as well. How to drop index? So I'd write drop index name on table name. We don't need to give the name of the column here. So this is how we drop the index. So this is just few things about the indexes. We'll talk about indexes tomorrow again, and then also we'll talk about the query execution plan, some of the important operators there. This is what we are going to talk about. And so right now what we are trying to do is that we are trying to create a base of all the different type of SQL Server knowledge that we can